Okay, so let's make a sketch of what's going on in this problem. We're told that this is a rectangular wire loop. This, it's got a length of 10 centimeters, width of 4 centimeters, and it carries a current, let's say, going around this way of 3.5 amps. This thing's in a region of uniform magnetic field that goes through at a particular angle. And the question is, what's the magnitude of the torque that's exerted on this wire loop? Okay, so what do we need to figure out? Well, we could use the expression F is equal to, or rather dF is equal to I dl cross B. But given that this is a wire loop in a uniform magnetic field, we can use the relationship that we derived in class between the torque and the magnetic field, that is tau. The torque is equal to mu cross B, where mu is the magnetic moment, I times the area vector. So by far and away, the easiest way to do this problem is to calculate the magnetic dipole moment of this wire loop. Okay, in order to do that, we just need to calculate the currents given, 50 coulombs per second. And then we need the area. Well, for a rectangle, it's pretty straightforward. Probably the only tricky thing is we make sure we work in consistent units. So we'll put the length and the width in as meters. There we go. Okay. And so we can just multiply these things together, and we find out that the dipole moment, magnetic dipole moment for this loop, is 0.014 coulomb meter squared per seconds. Okay, so that's the first step in what we need to do. Now, in order to calculate the torque, remember we want tau is equal to mu cross B. And if we are just interested in the magnitude, we can realize that this is mu B sine theta. And B is a constant in the problem, so the question is, what's theta? Well, if we look at the specification of the problem, it says that the magnetic field is directed 40 degrees above the plane of the wire loop. So let's take a side view. Okay. And we're told basically that the B field points up through the loop like this, and this is 40 degrees. Now, I might be tempted to use 40 degrees for the sine theta, but that's not right in this problem. Remember, the magnetic dipole moment is directed in a plane that's perpendicular, or in a direction that's perpendicular to the plane of the loop. That is, if you have a loop and a wire going around, the magnetic dipole moment points out of the loop. So that means that the direction of mu is normal to the loop. Okay, just using a very simple amount of trig, we can figure out that the angle between the B field and mu, which is what we need, is 50 degrees. Therefore, the torque in this case is equal to mu, 0.1014 coulombs meter squared per second, times B. If we just look and see what that was, read the problem. It's 0.675 Tesla. So 0.675, and then for units, newtons, seconds per coulomb meter. Okay, times sine, in this case of 50 degrees. Work out those calculations, and we find the torque is 7.24 times 10 to the minus 3 Newton meters.